My name is Pavel Augustinov. I'm Director of Code Intelligence here at GitHub. I came over with a similar acquisition, and I work, among other things, on the CodeQL tech for security research. Alvaro, who is here with me, I hope. Yeah, so what we were going to talk about is actually quite an interesting exploit chain in the Apache Druid ecosystem. It was discovered a little while ago, and of course patched. We would not be doing live querying for zero-day vulnerabilities necessarily. Alvaro has a great explanation lined up for what the exploit chain looks like. It's a good example of how to combine a number of tools that we often use in the security research community to get into our target and to send the payload that we care about. I would like then to show you how we can use CodeQL to do variant analysis on these issues, finding out whether there are any other potential risks lurking in the Apache Druid ecosystem, and generally showing you how to use it for a kind of example-driven audit of a large code base.
Yeah, I don't know if you are familiar with previous editions of this LiveQL kind of series. The first one was led by Aditya and Nico Weisman, and they talk about basically some memory corruptions and how they were able to model them with CodeQL. In these episodes, what we want to do is basically pair a security researcher, in this case myself, with a CodeQL expert. So they can pick, we can pick our brains mutually and try to model some security knowledge or patterns with CodeQL, and then being able to find variants of some known vulnerability classes, maybe more variants of a specific CV, like is going to be the case in this episode. So what we are going to do is basically, we are going to model CV 2021-25646.
Which, as you can see here, it's a remote code execution in Apache Druid. And basically, this is some sort of data flow from some user-provided data. In this case, some sort of JavaScript code, which flows into some script engine, probably Rhino or Nashorn. And in theory, Apache Druid is protecting itself by requiring some explicit configuration to enable JavaScript. So it's disabled by default, so an attacker, even if they can provide a script that shouldn't be evaluated unless the developers or administrators are enabling that. We can go and see that in the JavaScript programming guide for Apache Druid. And as they say it here, they're using Mozilla Rhino, and Apache Druid does not write to sandbox the evaluation of JavaScript at all. So it's going to run whatever we provide. So for those of you who are not familiar with Rhino or Nashorn, they will evaluate JavaScript, but they also offer some bridges into Java. So by providing arbitrary JavaScript code, you can also evaluate and run arbitrary Java code.
So basically JavaScript evaluation is disabled. So as the advisory reads, the attacker is able somehow to change this configuration and re-enable the evaluation of JavaScript. And we will see how they can do that later. So Apache Druid is basically a high-performance real-time analytics database, and it will offer some JavaScript features in order to extract data using JavaScript functions, filter data, aggregate data, and so on, right? So I think with that, what I did basically is that I download, let me go. Sorry, I was in the middle of something else. So I downloaded 3 versions of Apache Druid. The one that was vulnerable was Apache Druid 19, and then we are going to change into this version, and they are kind enough to provide some Docker distribution. So we go into distribution and then Docker, and basically we have, let me make this a little bit bigger, we have some Docker container that we can start and play with. So the only thing that I changed from the default configuration that you can go and download yourself is basically I changed the Docker Compose and enable or change the Java virtual machine configurations in order to enable the debugging agent and expose it in port 5555, which is later exposed in 5559, right? So basically, when I start, Docker, it's going to start up Druid and all the requirements, and also it's going to start, as you can see here, the debugging ports in order for us to be able to debug and set breakpoints and see what is going on, right? So the next thing that we are going to need is basically start an proxy, an interceptor proxy. And for that, what we are going to do is we are going to use Burp, which is basically the most, probably the most popular interceptor proxy. And in the latest version, they have this nice feature where they allows you to open a browser, which is automatically configured to go through Burp, right? So the only thing that we need to do here is see if Apache Druid is already running, and this seems to be the case. Maybe it's not fully loaded yet. Let's give it another try. And okay, so in addition to that, I found a very interesting Red app, which is going to walk up through the process of reproducing this vulnerability, right? So let me see. So here we have how we can build our own test environment. So we already start up a Docker container. And now, in order to reproduce the vulnerability, what we need to do is basically load some data into this analytics database. We are going to load it from local disk to simplify the setup and the environment. And then we are going to basically load some data from local disk. And at some point, the data is going to be shown to us and we can filter that data, right? So by adding some column filters, what we can do is what is going to happen is that basically the front end is going to send some request to the backend saying how to filter that data and send back some sample data. So in the request, it should appear something like a filter with the selector type. And apparently, we need to change that into JavaScript type in order to be able to add a function. And then within this function, we are going to be able to execute arbitrary Java code. So I think we can try that and see if it works. We should have everything we need. We have Apache Druid, so we are going to load this data. As the Red app says, we're going to load it from local disk. And I'm gonna connect this data. I think it was from something like quick start tutorial. And then let's feed some JSON files. Okay, there we go. So this is the raw data. Now we can parse it. And you can see here all the data. These are a huge amount of rows here. And we can now filter them, right? So what we want to do is see if Burp is getting some requests, and we can see that we're getting some requests, and some of them are to the Druid indexer version 1 sampler, which is the vulnerable endpoint. And basically now we are going to add a column filter. And we are going to say something like this and send it or apply this filter. And as you can see, we got some new requests that were sent to the backend. So we are going to inspect these requests and see if they fit what we saw in the red app. So let's send this one to repeater so we can play with it and change it and modify it as we want. And basically, this looks very similar to the one that we saw in the red app. It's a post request to the sampler endpoint. And then we have the data that we are basically, or the sample data that we are filtering. And we have some data schema with some transformation spec. And within this transformation spec, there is a filter which is of type selector, which matches what should be here, apparently. Okay, I think with that, we can try and see if we can modify this. Like, for example, if we change the type to a JavaScript type, we can send it like this, and we will get an error because basically the JavaScript dim filter, which will be very useful for later analysis, does require a function field, right? Not a value. So, okay, let's play with that, add a function here. And I think we can name our parameter as we want. And then we can put any arbitrary Java code here. Like if we want to run a process, for example, we are going to use the Java lang runtime get runtime, and then we are going to run some process. Let me use single quotes instead. And I don't know, we can maybe touch and create a TMP pwn in order to prove that this was executed. So if we run it, it's gonna fail, right? The reason for that is that, as we mentioned before, JavaScript is disabled. This is the default configuration. And even if you can reach this JavaScript evaluation, there is a control before which will prevent the evaluation of JavaScript code. So, by the way, Pavel, this will be very useful for you later.
I was just looking at the stack trace. Exactly, that's what I ultimately want to explore later on, right? So we started sampler resource and we go through.
Yeah, so we have some code in Google Inject and then move into Jersey. And then the first time that we hit Apache Druid is in the sampler resource. So this is going to be our entry point, probably this post method here. And then it's like going through some methods that are very similar to the ones that we saw in the JSON. So they are probably going down in this object bound from the HTTP request. Yep. And at some point they are like constructing a filter, which is being unmarshaled from probably this piece of JSON over here. Okay, so we skipped a little bit of the reproducer here on purpose, and it's this little piece over here that is going to do all the magic. So let's just copy this to our.
That's an empty string key for the JSON object that maps to. Okay, carry on. That's
it's basically exactly that. So it's an empty or an empty named property with another property that is a Boolean called enabled. And then if we just copy it here and we try it again, we can see that, well, there is.
You need a capital runtime, Java lang runtime, possibly.
Java lang runtime, yeah.
But yeah, it's clearly actually running the JavaScript now. So
yeah, so yeah, exactly. So it's a proof that it was running JavaScript, and now the filter didn't return anything because it was not actually filtering anything. And now we should be able to go here and see if it worked. So we have some containers here. I think the one that we want is the coordinator, the Apache Druid coordinator, and then we can do something like this, get into the Apache Druid container. And now if we list TMP, we should have our pwned file. So apparently, yeah, we got remote code execution. And now we need to understand why this little piece worked here. So for that, what I'm going to do is I'm going to start IntelliJ. And first of all, I'm going to set a couple of breakpoints. The first is going to be in the, a couple of breakpoints. The first is going to be in the REST endpoint. For that, we can just use the stack trace that we saw before, or another nifty trick is that if you're using IntelliJ and go into the endpoints tab, you can basically search for endpoints because they are mapped here to the right controller methods, and you will see that the version 1 sampler is mapped into the sampler resource. So we can go here, connect the debugger, because otherwise we are not going to get anything. And then we can set a breakpoint here where we are basically, this is basically Jack's RS endpoint, resource endpoint. So this piece over here is bound from the HTTP request and can be controlled by the attacker, and then is passed to this check here, and then we are invoking the sample method. Right, so the other piece that we need is, remember that class called JavaScript Dim Filter. This is where we were getting the error, exactly this one. Yeah, the JavaScript is disabled. So we want to put another breakpoint here. And now we are going to send the request again. Let's see if we hit the breakpoint, and yeah, that's the case. So we are now in this entry point, basically. So that proves that this is the right entry point for our data flow. And if we continue, we hit the second breakpoint where we are checking what's the actual configuration of the JavaScript engine, right? So if we check the config over here, we'll see that it's actually enabled, right? So why are we being able to control if JavaScript is enabled or not? So in order to understand that, we need to go up a little bit and see.
Where did the config come from? That's kind of the question, right?
Yeah, exactly. So config is basically defined in the JavaScript Dim Filter constructor, which is managed by Google Juice. So it's basically injected, right? So if you see the parameters of this constructor, we have 4 of them that are annotated with JSON properties, and we are already familiar with some of them, like for example, dimension and function. If you remember, they were part of our payload. But then we have 2 others that we didn't use, the extraction function and filtering tuning. Apparently, they are nullable, so they are optional. And then we have this JavaScript configuration. So this is what is being used to decide if we should be able to evaluate JavaScript code or not.
But that doesn't come from the JSON, right? That's just injected by Juice?
Yeah, so that's what I thought when I saw this piece of code for the first time. And then I went and checked the documentation, because that's what we need to do when we don't know what is going on. And if you check the documentation for this Jackson inject, so I don't know, your guts tells you that this should be injected from the dependency injection container, right? But if you read the documentation, it says that it will be injected. Okay, so far so good. Based on the configuration of the object mapper. Usually, yeah, it's not always, but usually property is not deserialized from JSON. Although it's possible to have injected value as default and still allow optional override from JSON. So apparently, it should be able to pick from the dependency injection container or framework. But if you provide it from JSON, it will override the injected value, right? So now this was added in version 2.9. Now you can control that. By default is auth boolean is true, translates to true, so it allows to be overridden. But if you go back to the documentation one version before, for example, here, this was not here, right? So probably they choose this insecure default because they wanted to keep some backwards compatibility, right? So that's normally some enemy of security at some points. So what we know now is that because this annotation over here is not using this opt, I don't remember the exact value, but something like
use something or other,
yeah, something true. Then it's allowing the data coming from JSON to actually override this configuration.
So the reason that we needed an empty property name is that we don't have a JSON property annotation here, and so that's how you get into it?
Yeah, exactly. So because Jackson doesn't know what are the names of the function of a constructor in this case at runtime, because this is something that is reset at compile time, then you need to actually annotate these parameters here with the JSON property. But if you don't have a JSON property value, apparently the framework will pick an empty string as the name. So this is
like a odd choice.
pretty awesome. Yeah, I mean, the way it works, I don't know, if I were a developer and I will expect Jackson inject to pick the data from Juice, Google Juice in this case, and not from JSON provided user controlled data.
Mm-hmm.
So I think that's it. So we have a vulnerability that is two parts. The first part is basically an injection vulnerability, which is enabled by a data flow flowing from some untrusted data that can be controlled by the user into a Rhino evaluation sink, which is not sandboxed. And apparently they decided that instead of sandboxing this evaluation, what they wanted to do here is basically put all these JavaScript evaluations behind configuration setting. So this is kind of dangerous because developers maybe need to evaluate JavaScript for some specific reason, maybe during development, and then they can leave that enabled and open the application to remote code execution. So I think it's better to sandbox the engine. Anyway, the second part of the vulnerability is that an attacker can actually change the value of the JavaScript configuration. And that's some sort of mass assignment vulnerability. If you are familiar with this old vulnerability class where you were able to bind properties from the HTTP request into nested, deep nested objects of the object graph. And I don't know, what do you think? Do you have all you need to model?
There's two very different, very separate things here. I mean, firstly, of course, the flow from web request to JavaScript engine is quite interesting. And one question I have is, in this case, we hit one of those precondition checks that ensured that the JavaScript config was enabled. Does that happen on all paths, or are there some paths which maybe reach the JavaScript engine without a check? That would be problematic.
Yeah, so I think that's a great question for CodeQL. So we can actually try to find out if there is some evaluation which is not guarded with one of these checks. Yeah, that would be awesome.
Let's definitely do that. And the other thing, the other part of this is this Jackson inject gotcha. I wonder what else is annotated with Jackson inject that we might be able to override from a JSON payload that we send, and what other fun things we can do with that. But yeah,
so I think there are two ways of doing that. The simple way should be just look for constructors or factory methods with this Jackson inject annotation, and don't check where these objects come from. So it may trigger some false positives in the sense that that data may not be bound to an HTTP request. But the other more complex query, I don't know if we will have time for it, is to inspect the object graph of this, in this case, for example, of sampler spec, because this object graph can be controlled by the attacker, and then find if any of the nested objects contains a constructor which using this annotation. But yeah, let's see if we can get to it.
Let's dive into the QL part. So let me share my screen real quick here. Are you okay with the font size? It looks roughly right, but I can zoom in a little. Let's see how we get on. So for those of you who are not familiar with CodeQL, it's essentially a query language over code. It allows me to write simple queries or complex queries, or indeed queries that leverage complex analysis libraries in order to do things like the taint propagation tracking and examinations that we just talked about with Alvaro. So what I've done here is that I've downloaded a database representing Apache Druid at a particular moment in time. I did it a few days ago. It's a relatively recent version. And I've loaded it into VS Code with the CodeQL extension. At this point, I can run simple queries. Of course, select hello world is the first query that everybody writes. But in practice, I'm actually interested in querying Java code. So I'm going to import our Java library. And at that point, I get access to all of the different concepts that are defined in it. And I can write all sorts of interesting queries. So perhaps one thing to start with is to focus on the JavaScript engine part of this. So Alvaro showed us in the debugger how request data was able to get to the Rhino compile function method. Let's see if we can find that call in my database. So I'm going to use the from clause to declare some variables. So I have a call, and if I was to run this query from call, select call, I would simply get a list of all the calls in the program. Of course, I don't actually care about all the calls. I want to limit that result set a little bit further. And so from a call, I'm going to jump to the thing that is being called, and I'm going to jump to its declaring type. I'm going to jump to its package, and I'm going to look at its name. And I'm going to, in particular, be interested in when that contains the substring JavaScript. Now, here I'm kind of exploiting my knowledge of the Nashorn or of the Rhino JavaScript engine, which is in the package org Mozilla JavaScript. Mm-hmm. So what this should do if I run it is show us all the places where Apache Druid calls into one of these Rhino APIs. And so we can see over here there's 70.
Not that many.
It's not that many. Yeah, we could look at all of them in detail. Of course, we should look at a few just to build our intuition. But here is a call to get local, which is on context factory, which is indeed in org Mozilla JavaScript context factory. So that is indeed what I'm after. There's sorts of other API methods that we call, but here is kind of the interesting one. This is a call to compile function. And this function variable is the source code, which potentially might have come from a request. And of course, that's kind of how we are interested in finding it. So that's good. I'm going to just lift this into a little helper class. I'm going to define a class called JavaScript API. And I'm going to give it essentially the same logic that I just had over here. And at this point, I can use that for further queries. If I was to run this query, that should give me exactly the same result set. I merely have a reusable piece of logic here. Okay, so we've got the sink of our taint propagation problem. Let's think about the source. So as Alvaro showed us, that was the sampler endpoint of a JAX-RS web service. Now, there's there's a couple of ways we could model that. Of course, we could look directly for methods annotated with post. We could look for the specific class, but actually we already include a whole bunch of modeling in the CodeQL standard library, including modeling for JAX-RS web services. So I'm just going to leverage that. I'm going to import my flow sources library, which defines lots of interesting APIs that typically provide security sensitive data. And let's explore what's in there. A particular class I care about is called remote flow source. So if I briefly hover that to get the doc, it's a class that represents any sort of source of remote user input. So typically that's request parameters, request bodies. It can be things you read from a socket. Let's run that query and see what the potentially reachable attack surface is for this particular code base according to the models in our library. JAX-RS, of course, is common enough that we have good modeling for it, but it's easy to extend the remote flow source class with additional definitions if we wanted to add support for a new framework. So we've got 440 results. Those are things where data comes from allegedly some remote source. Let's take a look. So this input parameter indeed is in a post request handler, and so comes from the post request. Similarly, the start parameter, yeah, come again?
Yeah, so this is basically the attack surface for the application, right? So those are all the places where an attacker can, try to knock at the application.
Exactly. Certainly,
from a security point of view.
In terms of JAX-RS, this is a pretty good approximation. And of course, there's other interesting stuff. So, for example, this HTTP servlet request, which represents the context, gives you access to lots of other things about the request, also can be a source of potentially attacker-controlled data. So we include that. So there's 440 of these things. Now, I'm actually interested in perhaps narrowing down, at least in the first instance, to the sampler request, which we saw before. So one way I could do this is to say, if I take the location, and I look at the file, and I look at the base name, then as I think I recall.
Yeah, that's correct.
Sampler resource.java was where it was defined. So if I now run this, take a couple of seconds, and it gives us exactly one result, which is the sampler spec argument where you started your exploit, Alvaro. So that looks promising.
That's our entry point.
Okay, so now the question is, how do you connect them? How do we get from this remote flow source to a JavaScript API call? And again, I'm going to lean heavily into our standard library, which provides lots of primitives for building up this kind of analysis. After all, taint propagation analysis like this is one of the staples of security research. Yeah. So I'm going to pull in SAML code Java taint, data flow taint tracking. And the taint tracking library that we have actually allows me to look for data propagation between arbitrary points in the program, no matter how far removed. But we do need to configure it. Of course, in general, if I asked, give me all pairs of points in the program where data comes from one and goes to the other, that would be way too many results, and we would not want to look at them all. So in order to configure it, I actually have to provide a little extension class to the library. So I'm going to basically subclass the taint tracking configuration type, which allows me to specify what exactly I'm interested in. The first thing that I need to do is provide some kind of tag that identifies this particular analysis. It just has to be unique. It doesn't really matter what it is, but in principle, I could have more than one different taint configurations in the same query if I was tracking multiple things and talking about their interplay. So it's just really a tag for a particular instance of the taint propagation tracking. The next thing I need to supply is an isSource predicate, which tells the library which data flow nodes we want to begin our tracking at. And this is relatively simple. Again, I'm just going to basically lift the query that I wrote there. The source should be a remote flow source. And if I look at its location, at its file, let me just copy paste this rather than typing it all out again. Should be that. So that's half specified. The other half is what are my sinks. In this case, I'm going to say my sink is what I get if I take one of the JavaScript APIs in the database and look at an argument of it. So this is the type that we defined up here, the one that matches calls into the Rhino API. And what I'm doing is, for any such call, I'm looking at the argument. I'm saying, well, that argument is potentially at least a sink for my data flow. What I always find useful when I build up configurations like this is to validate that each piece works in isolation in order to build confidence that I haven't made a mistake or a typo or something like that. So I'm going to use the quick evaluation feature to just ask to inspect all of the values in this isSource predicate. And unsurprisingly,
we have our 440 results.
Well, I say unsurprisingly, I am actually a little bit surprised because I was hoping that it would be restricted to just our one entry point. So what's going on here is actually kind of interesting. Because this predicate overrides the predicate from the library, I'm actually picking up other configurations in the library that use all of the remote flow source predicates. But I was able to confirm that this predicate for this configuration is actually going to indeed be the one I care about.
So what you did is basically you evaluated or quick evaluated the body of the predicate and
exactly.
not
I
the
just
whole
selected those two things, and I triggered quick evaluation, which basically says, show me all the variables that satisfy that formula in particular. It's a very useful trick to know if you're trying to debug a particular.
I knew that you could evaluate a predicate, but I didn't know that you could evaluate the body of a predicate. That's
it's pretty. You can do
even just one line.
Stuff. So if I select just this bit, it'll show me all of the data flow nodes in this file.
So any variables that are not bound are basically treated as
exactly. We're looking for values that will satisfy the formula I selected.
That's awesome. Yeah.
Let's also quickly validate the isSync predicate down here. So I'm going to trigger a quick evaluation on its body. And hopefully we'll get some results. We have quite a few. Actually, I'm not all that fond of all of them. So this function, I definitely want to consider as a possible sync. And I'm not quite sure what this argument to compile function does, but maybe it's interesting. But a number is not really that useful as an injection vector for RTEs, right? And similarly here, we're passing a number in. Even if I could control this from my request, that wouldn't be that interesting. So I'm going to restrict it a little bit. I'm going to say sync.get type instance of type string, which is Java-lang string. So I only want to look at the strings that I can inject into Rhino, not other things. Again, let's quickly double check that I haven't done something silly. Hopefully we'll get fewer than 87 results. There you go. It's just 14. There's the function, this thing, which I assume is vaguely interesting. It might not be, in which case we could filter it out. And a bunch of other arguments to compile functions. So that looks good. That looks like a good set of things to me. Now, I've defined my configuration. How do I actually use it? How do I ask for the chain propagation from source to sink? Well, this bit is a little bit boilerplatey. So I need to write from dataflow node source, dataflow node sink. There is a configuration JS which has flow from the source to the sink. Select source sink. So what am I doing? I'm instantiating my custom configuration, and I'm asking it to tell me about all pairs of sources and sinks between which it's able to track flow. Let's run the query, and hopefully we'll get at least one result, because we know there is a flow propagation. After all, you showed us the exploit.
So we have a question in the chat. Does the evaluation works at the abstract syntax tree level while it's running the query?
Yes, in a slightly over-convoluted yes. I say that because we have a representation of the abstract syntax tree in the database, and you can query it. When I talk about things like calls and when I talk about methods and types, all of those are things in the abstract syntax tree. The reason I hesitate is that actually the data flow and chain tracking analysis is done at a layer above that. So we superimpose a graph of data flow nodes on top of the abstract syntax tree. And then data flow propagation happens between those. That's just convenient because sometimes a single AST element doesn't map to just one data flow node, but multiple, sometimes the other way. It's handy to have an extra level of abstraction on top of that for that reason.
Makes sense.
I have 0 results. Perhaps that's a little bit surprising. After all, we know there should be one result. But ultimately, when we do global data flow propagation analysis like this, it's always going to be an approximation in some sense, right? It's going to make a best effort to track the information, but at some points we have to make trade-offs. We have to choose precision over extreme amounts of noise and things like that. And so sometimes we may miss genuine flows like this. I think this is a good opportunity to talk a little bit about how we would potentially diagnose and debug this. So I know there is a flow. I don't get it from the library. What do I need to add in order to actually get there? So what I'm going to go ahead.
So in the chat, they said if it's possible to have access to the AST representation, and Jaro pointed out, which is true, that we even have an AST viewer that maybe we want to show, maybe now or later when you have.
That's a great idea, actually. Yes. So if I go to this file and I trigger the view AST command. So that'll actually run a query to extract the AST structure for this particular file and show it to me in this little tree view down here. So the top level AST node is something that represents the compilation unit, and it has a bunch of imports at the top. So imports preconditions and resource filters and sampler resource and all those kinds of things. But the interesting thing is then that here we have a class node, which is the definition of sampler resource. It has a bunch of annotations that tell us where it is, and it has a method called post, which itself has a bunch of annotations, and it has some parameters that we can look at. So it has the sampler parameter, and it has a block statement, which contains a return statement, which contains a method access, which contains another method access. So the top one is this call to sample at the back here.
So this is really handy when you're writing a query and you're new to CodeQL. Maybe you don't know how a specific expression or part of the grammar is being translated into or matched by CodeQL, and then you can go here and see, okay, this is a type access, for example, or a bar access or string literal, and then use those. And
those are actually the CodeQL API names. So if you queried for all block statements, one of the things that would come up is this one. If you queried for all type accesses, then this one would come up.
That's awesome.
yeah, it's a great way of getting a feeling for what a piece of code looks like in the AST, and then you can think about how you want to match it and generalize it in your query. But I was interested in figuring out what's missing in our data flow propagation. How can I actually get the flow that I know is there? And this is more art than science, I have to say, because there are very many different things that the program could be doing in order to prevent us from finding a particular flow. And often, as you try to explore that, you can get into a situation where you're asking for very large result sets, and that becomes hard to audit manually. So here is something that often works for me. I'm going to change my definition of isSync to be just any. Any is the way that you say true. It's a predicate that holds of all inputs. And so now what this configuration says is I want to start tracking at this source, but I'm interested in any possible sync that you manage to reach. And so we can use this to kind of explore the fringes of how far we've tracked the tail propagation. It's worth noting here we've already restricted the source to just match one node. If you make the syncs much more permissive, it's often a good idea to restrict your sources in order to avoid just having an explosively large result set that will prevent you from seeing what's going on. So here's my results. 29 pairs of nodes, which means there are 29 places to which we managed to track this particular piece of data. And the first one, well, it corresponds to itself. Yes, if this is untrusted data, then it is untrusted data, yes. The second one corresponds to kind of, in another method somewhere, the qualified this of Kinesis sampler spec. And I guess you can sort of imagine how this might have happened, because sampler spec, if I just jump to its declaration, is just an interface. And so it will have a bunch of implementations, of which Kinesis sampler spec is going to be one, indirectly, of course, because why would it be simple? And so if we happen to get one of these, then the this method, or the this access on that type would be tainted. That makes a lot of sense. And then if we look here, this IO config thing is actually a field in another type of sampler spec. So what this is telling me is we managed to track to this type of sampler spec, and therefore the this access which implicitly qualifies this field is tainted. So that's a little bit confusing, because the display string here is this of something.field. What this is actually telling us is it's a this access that qualifies a field. It's not telling us the field is tainted, crucially. And you can see quite a few other examples that are basically like this. Lots of field accesses where the implicit this is tainted, but the field access itself is not. And so actually, this is precisely where things break down here, because if you recall what we're doing, we've just deserialized one of these sampler specs from JSON. That's some kind of deeply nested object with lots of fields and other things stored on it, and ultimately all of them are under the control of the attacker. It's not just some. So one thing that we could add to our query is something that says, if you have tracked taint to something that came from a Jackson deserialized thing, then any field access on that should be considered as tainted. So let's talk a little bit about how we're going to do that. We're going to first identify all the types for which this holds. We're going to have a predicate that gives me a reference type, and I'm going to call it Jackson deserialized type. And Now we're going to have to define this slightly recursively. I guess to get started, we could say that from any remote flow source of a particular type, we can deduce that type is potentially Jackson deserialized and attacker controlled. So we could say result is any remote flow source s.get type. That's not going to be quite enough, because in this example, the type of the remote flow source is sampler spec, which is an interface. Actually, because it's annotated with JSON type info, any subtype of that interface could potentially be instantiated through JSON using the type property to give the concrete subtype. Mm-hmm. So we're going to add another possibility to our predicate here. We're going to say, if we have a Jackson deserialized type already, then a subtype of it is also potentially Jackson deserialized. So that'll cover the interface case quite nicely. We need one more step, which is that if we have a Jackson deserialized type and it has a field, then the type of that field is potentially also Jackson deserialized. So this is us kind of going through the object graph, right? We're looking.
So this is a little bit confusing for someone like me that comes from like imperative programming language world. So what are you doing? What you are doing there is some sort of I don't get the word now. Recursion?
Yes, it's definitely a recursive computation because Jackson deserialized type depends on itself. You can kind of think of it as us finding more and more values that satisfy this particular predicate. So the starting point is just this bit. Let's quick evaluate it and look at a few examples. So in the base case, in the starting point, we get things like HTTP servlet request. Well, actually, that's not really a Jackson deserialized type, is it? It's just something that's a parameter, that's a remote flow source. Yes. Maybe I should have phrased this differently. Let's do it slightly better. Results. So what was characteristic about sampler spec is that it was annotated with JSON type info. So if I take an annotation of the type which I'm going to claim is Jackson deserialized type, and I get that annotation's own type, I get the name.
Mm-hmm. So I think your first approach was better in the sense that from a JAX-RS standpoint, you can use Jackson, but also JAXP for XML, or you can bind to raw strings, or maybe some simple objects. So maybe just start with anything that is the argument of a JAX-RS endpoint method. And maybe as an evolution or an improvement of this query, you can subtract or constrain it to not be some of the injected types like HTTP servlet request or not.
Yeah, that makes sense. But you're right, of course, that ultimately being a remote flow source is much more closely what we're interested in than being Jackson deserialized. Maybe there is some Jackson deserialization that happens entirely locally, independently of the network request, in which case, yes. So this formulation will actually do that. It'll do a little bit more, as you say, because it'll pick up HTTP requests and stuff like that. But it'll take
that's fine for it.
Yeah, it'll take the type of any remote flow source. It'll take any subtypes thereof, and this will give us the interface to implementation step. And it will take the types of any fields of the classes that it's reached, so that we get the nested structure of the JSON payload. Now we've defined this predicate, but we haven't used it yet. So we need to make use of it somehow. And ultimately, what we're trying to do is extend the taint tracking to have some additional steps in it. So I'm going to import that extension point. Sample code Java data flow steps. And the way that I extend the taint tracking analysis is by providing a subtype of the additional taint step class. So let's say I'm going to call it Jackson field step, and I need to provide a step predicate. Which basically tells me when the library should consider flow from A to B to be given. And what we're trying to model here is basically for a field access like this, if A is of one of these Jackson deserialized types that we want to do the extra tracking for, I want to say from A being tainted, we can deduce that the field access to B is tainted. In particular, we only want to do that for field reads, actually, so we can do that as well. A should be the field qualifier of B, and if I left it at that, then if I have a field right like this, we would still think there is propagation from A to B, even though B is being overwritten here. So I'm going to do a downcast here to field read. So there's only a flow propagation step if the field is being read rather than written.
Mm-hmm.
And of course, I want to say a.get type is one of my Jackson deserialized types.
So I think this get field qualifier is a good example of what you explained before, that the data flow library is an abstraction of the raw AST in the sense that a field doesn't need to be qualified, and you may have field accesses in the AST that are not qualified, and in this abstraction we are always making sure to qualify them somehow, right?
Exactly. So we can synthesize a kind of a implicit this qualifier on fields that don't have a qualifier, and that's why we can ask for it. In the pure AST, there would be no qualifier, and so we couldn't necessarily reason about this, which is exactly right. So I think at this point, if I run the query again, maybe I should have, actually let me cancel that, because I've added quite a permissive taint step up here. I'm going to undo my changes to the sink. So we're now, again, only looking for examples that go to my particular sink, or rather to the sinks that we're interested in as JavaScript APIs.
So we are looking from data flows from the parameter of the sample resource method flowing into any Rhino API argument, call argument, and then enabling the data flow by considering taint steps when there is a field access from a qualifier to the field access itself, when a field access read itself, but just limiting that not to all types, but just those that comes or can be bound or unmarshaled from an HTTP request, right?
That's right, yes. And we could improve the precision of this predicate, but it's a reasonable starting point. And as we can see, we actually found 6 results now, which correspond to different source sync pairs.
That's interesting.
So from sampler, we got to this aggregate, to this reset parameter to compile function, to this combine parameter to the compile function, to this function, to this function, to this script. Now, you might wonder how. Obviously, in the debugger, it was sort of easy to see because you had the stack trace and you could see how the data propagates. Here, we're just being told that, yes, we found flow, but we, of course, want to look at it. So there is a slightly formulaic rewrite of this query that will allow us to expose what the flow path is. So if I just do a couple of mechanical modifications, so we're going to query for path nodes, we're going to query for has flow path rather than has flow, and we're going to change a little bit the pattern of what we're selecting.
So is this some sort of convention to specify the select statement?
Yes, exactly. Certain forms of select statement can be interpreted in different ways. And here we're providing a select that can be interpreted as a sort of alert on, in particular, a path alert on your program. So the first argument will be the primary location of the alert. That's where it would be displayed to the user. The string that we're selecting is the error message, but we actually have support for placeholders, so we're going to interpolate a link to the source into the string. And we're also decorating each error message with a source sync pair that corresponds to it. So this is what we want to display the path for. In order to complete the picture, I need to import Dataflow path graph, and I need to provide a teeny bit of metadata at the top, which basically tells VS Code that the result of this query should be interpreted as a path problem query or a path alert query. So let me run that.
So I guess once that you are familiar with taint tracking configuration, this is almost boilerplate that you can easily fill in.
Absolutely. This is mostly completely standard. The things that vary are the definitions of source and sync, and any particular extensions that you have defined for a particular investigation. It is quite verbose because there's quite a few things that we actually need to provide to the library, but the things that actually vary are not that complicated.
So there is some, I think, misunderstanding in the chat. I think they are asking why there is a variable called, or a class in this case, called JSConfig, and they thought if it's maybe some sort of JavaScript interpretation using V8, but JSConfig is just the name of the Dataflow configuration. In this case, of the taint tracking configuration. It has nothing to do with configuring any JavaScript engines or anything like that. So.
Yeah, so I could rename it to anything I like. As long as it's a unique thing that acts as a tag on the taint propagation, it doesn't really matter what the string is. It's simply something that represents a particular set of parameters or a particular instantiation of the taint tracking configuration library. Okay. So we have our 6 results, but now you can see they're displayed a little bit more prettily as kind of error messages rather than merely as pairs of program elements. And I can expand here to see what the paths are like. Actually, let me pick the right result. The one that Alvaro was looking at was probably something like this one. Let's take this one. So if I look at the paths, we start at sampler spec sampler. We check it's not null, but that of course doesn't change it. We go into the sample method. In the sample method, we access the data schema parameter, which, if you recall, is actually one of the nested objects in the JSON payload. And we pass it to input source sampler sample. Stepping down, here is that sample method taking a tainted parameter of data schema. Over here, we pass non-null data schema, which is actually something that happened in the method. We reassigned, or rather, we conditionally assigned data schema to this local variable. But of course, that still propagates it. So this might be the attacker-controlled value. We build an incremental index from it. We call the add method on it. Here is the add method on the incremental index that we built from the data schema that we produced. We call add to facts. In this add to facts method, we call get metrics. And then with the metrics, we pass them to factorize args. This is quite a long path. I mean, you recall seeing the stack trace that Alvaro showed you, of course. But ultimately, we can end up in making this dimension selector thing. And we take an extraction function value and we apply it, and we call get compiled script. This may not be exactly the right stack trace, actually.
Yeah, I think this is a different variant, a different path in this case, which is great that you were able to find it.
Which is
because
nice.
Yeah, in some cases when there is a fix by the vendor or by the maintainer, they only fix a specific path that is reported by the security researcher, and this is a great tool to be able to find other paths that bypass the mitigations.
Yeah.
So I think that if you collapse this, the one that you have opened in JavaScript structure, I think the one below in
it's the dim
JavaScript
filter,
Dim
of course,
Filter,
yeah.
it's the one that
Yes.
we analyze.
Yeah, so here is the path that goes there, and it goes through 21 steps in this instance before reaching it. So the interesting thing that we should perhaps briefly talk about is the precondition stuff, right? Because this path isn't actually a vulnerability, assuming you weren't able to deserialize a JavaScript config onto it, which you are, because of this check state. But if this check state call wasn't there, then it will be problematic. So one thing we could do is we could refine our query to recognize this and to suppress results where we have to go through a check state call. Let me show you how that goes. It's yet another, let me undo my rename from before, just so we have pretty names. It's yet another bit of extensibility that the taint tracking configuration provides. You can tell it, what are my sources? What are my sinks? But also, what are my sanitizers? At what point do I want to consider my taint to be safe because the user did something clever? So very similarly, I define a predicate called isSanitizer. And now let's think a little bit about how we want to phrase this, though, because it's not totally clear. This is just a call to check state. And in fact, if you look into it, it takes a Boolean and it will throw an exception if that Boolean is false. So it's not in a conditional or anything like that. It's just something that happens on the control flow leading up to the construction of this JavaScript factory. So I'm going to just copy this so we have a reference as I try to match it in QL. So this is what I'm trying to match. I'm going to introduce a, in fact, we saw down here that the particular type I want is called method access in our AST viewer. So method access check state. And in QL, this exists construct is kind of a way of introducing local variables within the isSanitizer predicate. So it introduces a new variable that I can now constrain. And how do I want to constrain it? Well, if I look at the method that it's calling, it should have a name check state. That's of course not enough. I need more. If I look at its 0th argument, that itself, so this will be that thing over here. And we can sort of see how that kind of thing is represented. So we have one method access which has an argument, another method access as an argument down here. So I'm going to cast the 0th argument to method access. And the method that's called there should have the name isEnabled without parentheses.
Cool.
So I'm kind of cutting some corners here. Of course, I'm not saying specifically that the check state method is on the preconditions class. I'm not saying the isEnabled method is on the JavaScript config class. But in practice, I think this is probably restrictive enough. Let's just validate by doing the quick evaluation trick again. So we see there are 7 examples, which indeed each call preconditions check state with a message of JavaScript is disabled. So it seems plausible that those are the ones that I should care about. So at this point, I've identified the calls which are relevant to whether something is safe. I now need to say what tainted nodes should be considered sanitized. And the answer is, if you're familiar with control flow analysis, the property we're interested in is that the call to check state, which ensures JavaScript is enabled, should dominate the tainted use, which is actually safe. So domination is a control flow concept. It basically means all paths to this use of the function field have to pass through a call to check state. And
so should be reachable from that other node, right?
Exactly.
In the basic
block,
kind
of be completely unreachable. And we can access domination analysis through by accessing the basic block of the check state call and saying that it dominates another basic block, which is the basic block of.
Oh wow, I never done something like this in CodeQL. So it's pretty awesome. I don't know. It's pretty awesome that you can mix data flow and control flow analysis together in the same piece of.
It's vital, right? Because in this case, there is no data flow from this line. Sorry, from the check state line to this. It's purely a control flow property that makes this safe.
Yeah, exactly.
And so the ability to say that some data flow propagation is sanitized because of a control flow property is actually really exactly what we want here, and it's very handy. Let's run the query. Now, if we're lucky, we'll find a couple of paths where they've forgotten to check whether the JavaScript config is enabled.
Well, in that case, you need to black out your screen very quickly.
No, unfortunately, there are no such paths. Fortunately, I should say. They have properly applied sanitization to all the paths. But wait, to all the paths starting in sampler resource. What if we now broaden to all remote flow sources? Are there any other ways of getting to the JavaScript APIs without passing through a check state check? Well, we can find out. And I mean, it probably won't come as a surprise that there won't be. But in principle, this is a good way of building confidence that we've done it properly. And just to finish building confidence, there are no results for this query. But if I comment out my sanitizer again, should see more paths, more ways of triggering maybe the original exploit of reaching the JavaScript API from a JAX-RS remote flow source. So before we had 6 results, and with this more broad formulation, we have.
So we are extending now the analysis not just to those reachable from the sampler spec endpoint, but from anywhere that can be controlled by the user. And
exactly. So you can see we have 19 results rather than 6. And indeed, here is another source, this task thing, which is passed to assign task, which apparently through some path of 32 steps can reach this bit of JavaScript API and be executed there. But the good news is there is somewhere along that path a control flow guard that ensures we are in a JavaScript enabled configuration.
That ensures that if the control is not bypassable, then everything will be fine.
Yes. So of course, whether the control is bypassable is highly interesting. I'm conscious we're a little bit over time compared to what we wanted to take. How are you doing, Alvaro? Do you have another 5 minutes to look at the second part of the question?
Yeah, sure. I have all the time. I don't know, AJ, do we have 5 more minutes? I think it's okay. I think he commented that.
Go for it.
Okay.
So let's do the second part. The second part was to explore how far, or rather, how the Jackson inject annotation is used in this code base and what else it might allow us to do. So, as usual with CodeQL, the thing to do is to build things up gradually. Let's start by identifying parameters. In fact, what I'm going to do, I could just delete most of this since it's now a totally new query. I'm going to start searching parameters which are annotated with Jackson inject. P.get an annotation gives us an annotation that applies to the parameter P. From that annotation, I can take the type of the annotation, which is the annotation interface that has a name, and I'm interested in the case where that name is Jackson inject. So I'm going to run that query.
To be more complete. I think that you can also annotate fields, not just constructor or method parameters, but also fields. So can we just use a common parent from parameter and field?
I'm just going to jump to the parameter class in the library. So it has there's a local scope variable supertype. There's also a variable supertype. So yeah, we can use variable instead. So I had 231 parameters that are annotated with Jackson inject, and 261 general variables that are not just parameters, but also fields and other things. Let's take a quick look at a few of them. So that's kind of interesting because it's exactly the pattern that you were talking about, right? It's a JSON creator annotated thing, which takes an AWS credentials provider and potentially, if this is reachable, you could deserialize one of those providers. I don't know what you can do with one of them. I wonder whether we can help ourselves by being a little bit more selective. So we can maybe select the type of the variable.
So I can see there is, for example, an S3 client. So maybe you can point that client to a different S3 bucket or something like that.
It's possible. I've added the type to my query so that things are grouped by type effectively, and I can audit them a little bit more efficiently. So here is a Jackson inject, but this is presumably deliberate because this one actually has a JSON property annotation. So clearly they expect it to come from JSON and override the injected value potentially. Here we have a field, which is annotated to Jackson inject. I'm not sure what that does. You mentioned the S3 client somewhere. There's all sorts of interesting things.
I think it was close to the bottom. Yeah, maybe.
So there's. Can I order them maybe alphabetically? That would be a bit easier.
So it was the variable name, not the type. So okay, you have a second
Here's our JavaScript configs, which are potentially injectable in this way. And this is possibly the one that we looked at, or one of them is anyway.
Yeah, one of them. Yeah. So to make it clear, the fix for this particular vulnerability was to change some way in which Google Juice inject variables in this dependency injection container. So basically, no matter if they are not using Jackson inject with the proper value to prevent the overridden, the override of the value from the JSON string, it's now safe because they are just not enabling that at a higher level. So even if we find something here that looks like a vulnerability, it's not going to be the case because this is disabled in Apache Druid latest version. So just to as a disclaimer, that's reality in any 0 days. And Jonathan is asking for the fix commit. I will send it to you later because now we don't have access to the Twitch comments. I can read them, but I cannot write. So we'll send them to you. Cool.
So I guess at this point, the other idea that you had at the start, Alvaro, was that we could look at when a JAX-RS service reaches one of these things, one of these Jackson injected properties that perhaps are not expected to be injectable. That would look very similar to what we did before. Right? It would just be a data flow or a 10 tracking configuration going to type stuff. Actually, we have the pieces for that, don't we? I think we just need to say that, isn't it? Because our Jackson deserialized type predicate was already doing a object graph traversal to identify the fields which might come from Jackson. And so if we look for Jackson inject annotated variables which are of that type, then potentially they might have come from a remote flow source here. which is kind of interesting because now those are all the things that potentially are overridable from JSON. And it turns out to be most of them.
So in theory, maybe we don't have time for that, but you should be able to write an edges predicate and then be able to print the whole path from an entry point, from the root of the object graph into the nested property or nested variable or nested field, which is annotated with Jackson inject, right?
Mm-hmm. For sure. Yeah, we could do that.
Yeah, well, I don't know if we have time for that because, well, I don't know how it takes you. It can take me like a couple of hours, so probably it's a couple of
I'll
minutes.
take that as a challenge, Alvaro. Let's do it. So the way that you write path queries, so we already saw the slightly stylized version in which you write time tracking path queries, but of course, that's something you can do for any type of data, not just for time propagation. The way that you do it is that you provide an edges predicate and then a select of the particular type that we saw before. So what are our edges? Our edges are effectively, well, exactly the steps that I have over here, right? So let me see. So query predicate. So this is essentially what I'm modeling as an edge in the object graph, which we have shadowed in the Jackson serialized type thing. So there is an edge if from A to B, if B is a.getter subtype, or if B is a.getter field.getter type. So that will give me the edges that in the graph in which I'm, sorry, I didn't mean run query, I meant quick evaluation, because I want to see what's in this predicate. That will give me the graph in which we are doing this traversal up here to find what is remote injectable. And so we can see that there is an edge from object to basically everything, of course, because object is a supertype of basically everything. And there's 724,000 edges. That's a lot, but that's okay. Now down here, we're going to say, remember the pattern that we want to select. So it has to be a program element followed by our source sync pair, followed by a string. And what are our source and sync in this case? Well, the sync is the type of the variable, and the source is, well, a little bit weird. Sorry, that's nonsense. The source is any remote flow source type. It's going to format the document so it's a bit easier to read. So we've defined our object graph, and the traversals we're interested in start at remote flow source types, and they go to the types of the variable P. The variable P itself is annotated with Jackson inject and is one of our Jackson serialized types. So I'm in fact going to include a link to this source. Yes. I think that's it, Alvaro. Let's find out.
That's amazing. I mean, you can reason about code, writing queries little by little and having results, almost 1 million results in like 2 seconds. So it's incredible.
Inevitably, I've made a mistake. So let's figure out what that mistake is. So my edges relation looks reasonable. My alerts, so basically the problem is I get no alerts. That means something doesn't line up in my interpretation of things. Maybe I don't. What is wrong here? Can I spot it? So I've selected sources and sinks, and I would expect, for example, this to be, so from this interface to this Jackson injectable parameter of type AWS credentials providers, I should be able to see a path. And for some reason, it's not displaying it.
So Jonathan suggested that maybe the source and sinks need to be turned into Dataflow node types. I don't know if that's the case, because it's not a path. It's not a path.
I don't think that's necessary. I mean, the important thing is that they match up. The type of this source and this sink needs to be connected by this edge relation.
Yeah. So now our nodes are basically ref types, are not Dataflow nodes, are basically just ref type in our graph. The nodes are just reference types.
Yes. So let's actually have a quick look at the debug output. Maybe it tells us something useful.
Anyway, I think the audience would get the idea that you can actually build your own graphs, defining your own node types, and then you should get something similar to the path queries, where you are able to inspect all the nodes in the graph. And that's also awesome.
Let me just double check if this will do what I want. Okay, apparently there is something misaligning, and we are not quite managing to compute the paths here. I think you're right, Alvaro. The audience hopefully gets the idea that in the fullness of time, this is how you would see the path in the object graph. It's a very interesting combination of vulnerabilities that led to the problem here, and it's nice to be able to explore both at the same time.
Mm-hmm. Yeah, so I think that with that we can wrap up. I mean, it's been like 1 hour and 30 minutes. In that time, we analyzed the root cause analysis.
We fixed your microphone, and then we analyzed other stuff.
We fixed my microphone and internet connection problems, the camera and everything. Then we analyzed the root cause analysis of the vulnerability, and then we wrote a query to detect JavaScript injections in Mozilla engines, which I don't know if the audience is familiar with our GitHub Security Lab bounty program, but by submitting a query like the one that Pavel wrote, you can easily get a bounty. I don't know if Xavier can correct me, but I think it's between 2,000 and 4,000 or 5,000, depending on the impact, severity, accuracy, and other factors. But it's a very good way of spending a Friday afternoon in this 30 minutes. You could have earned like that amount of money. So I really encourage people to, up to $6,000. So I really encourage people to learn CodeQL, contribute queries, make our repo of CodeQL queries that are powering GitHub code scanning and lgtm.com more complete, and then earn some money at the same time. So it's a win-win. With that, I think we can wrap up. I don't know if also I wanted to comment that we are having a CTF. There's another great opportunity to learn CodeQL. This time is a CTF for Go. So you can check securitylab.github.com and check the CTF. It's live since I think a week ago, but it's going to be live for a month or so. And you can try to solve the CTF, and you will learn how to write CodeQL queries specifically to Go, but you can then expand the knowledge to other languages. Also, we had similar CTFs, if I remember correctly, for C, C++, JavaScript, and Java, at least from the top of my head. And also we have learning labs in the GitHub Security Lab site. So there are plenty of resources to learn CodeQL, and taking part of the bounty program is a great reason for doing so. Okay, so I think with that, we can call it. Anything you want to add, Pavel?
Yes, I think I just finally saw what I was possibly missing. So I'm trying one more run of this query.
We have a happy end.
Yes, because I've been staring at it and it's been bugging me. And there we are. The problem was I called this predicate edge rather than edges, and we specifically look for edges as the name of the edges predicate, quite sensibly. But you can see now, for example, here is what I was looking at before. From the task type, you can go to abstract task, which implements it. You can go to appenderator driver real-time index. That's an interesting name, but it extends abstract task. And then here you have thread, apparently, as presumably a field. So that's a refinement opportunity for the query, because volatile fields and JSON ignore annotated fields shouldn't participate in this object graph. We could fix that. But then from thread, annoyingly, we get to object, because that's a field on thread. And from there, we get to this. So, okay, this is an illustration of the importance of looking at the paths in the graph you're traversing. We should fix the edge relation to not traverse such edges.
Yeah.
But okay, I feel better now about
And this is a kind of query that is also very useful for finding gadgets for deserialization and other things, where you have to inspect the object graph of thousands of classes and see where can you go by invoking getters recursively. And this is also a great way of doing that kind of analysis. So with that, I think we can wrap up. Thank you very much for attending.
Thanks very much for your attention, everyone. It was great to be here, and we'll see you soon.
Yep. Thank you.